So here we're going to introduce the concept of the first derivative. And so we kind of started to hint at it in our previous notes where we were finding the slope of a line tangent to the curve x squared. And so we did that for a series of values. We walked through the slope of the tangent line at x equals 2. That slope was 4. The tangent slope was 4. And then on your own, you found the tangent slope at x equals 1 and at x equals 3. And so we had an approach that we could use, but it wasn't very efficient because we'd have to go through the same thing for each individual point. So what we'd like is a generalized formula. So something that we could just plug in whatever value of x we have, and we would instantly know what the tangent slope is. And so what we're going to do is we're going to take, for example, a curve like our f of x equals x squared. And we're going to take 2 points on that curve. We're going to take the point here, which is just x, f of x. So the input into the function is some value of x, and the output is f of x, whatever we get for plugging in that value of x. We're going to use this in a generalized format because we're trying to find a generalized equation. Then we're going to take a second point that is h units away from the point x. So basically what we're saying is we've got this horizontal distance h that we've traveled, and so as a result the x-coordinate of that point is x plus this distance h, and then the output is just going to be the result of plugging this new value into our function. So we would plug x plus h into the function and we'd get some new output, whatever the y-coordinate of that point is. And so there's a line that travels through those 2 points. We could draw that there. And so what we want to do is we want to find what is the slope of that line. Now, as it's drawn right now, that is not a tangent line. Okay, it travels through 2 points on the curve. We want the slope of the line that travels just through that point right there. So what that means is we have to take this point at x plus h, f of x plus h, and we need to move it so that it's closer and closer and closer to the actual point that we're interested in, the one that's right here. Which means we're taking this value h and we're making it smaller and smaller and smaller until eventually h equals 0. And so that's what we see here in this limit statement. So right here we have basically the slope formula. We're taking the difference between the y-coordinates, f of x plus h, minus f of x. Those are the 2 y-coordinates of the 2 points that we see to the right. And then we're going to subtract the 2 x-coordinates, x plus h minus x. And so we're going to subtract those y-coordinates, subtract those x-coordinates to get the slope of that blue line. But we want that blue line to not be the one that we see now. We want to shrink the gap between those 2 points until h equals 0. And so that's why it says the limit as h approaches 0 of this expression right here. Now if we were to just plug in 0 for h as it stands right now, and we'll do this specifically for this function f of x equals x squared momentarily, but if we were to plug in 0 right now, we'd see we'd end up with f of x plus 0, or f of x minus f of x, over x plus 0, since h now equals 0, so x minus x. And so we'd end up with 0 over 0, which is a problem, but it's a solvable problem, because if we recall, whenever we get this indeterminate form, we get this 0 over 0, that means that we have a removable discontinuity. And so what we're going to have to do is remove that discontinuity, and if we can do that, then we can apply our limit, and then we'll end up with this formula known as the first derivative of the function that we're working with. And so the first function we'll apply this to in just a moment is this function x squared. So there's a couple different symbols for indicating that we're looking for the first derivative, but the easiest way to do that is with this f prime or f apostrophe of x. And so that notation indicates that we are looking for, we're working with the first derivative, so the formula that represents the first derivative of our original function. So we're going to set out to try to find the formula for the first derivative of our function f of x equals x squared. So since we know what the values are supposed to be from our previous work, x equals 1, x equals 2, x equals 3, this will be a good test case for us to find a formula that we can then quickly verify that it is indeed accurate. So here's the general statement, just recopied from the previous page. The first derivative is equal to the limit as h approaches 0 of this slope fraction. And so I'm going to start off now specific to our function. So we've got the first derivative is equal to the limit as h approaches 0 of, now instead of this kind of general format, we're going to actually use x squared. So x plus f of x plus h is now going to be x plus h squared, because I plug x plus h into this function right here, and I'm supposed to square that number, minus f of x. Well, what is f of x? Again, that's our function that we're working with, x squared. And now in the denominator of our expression, for every function that we work with, and we'll see this in the subsequent examples beyond just this one, is always going to be x plus h minus x. So that's the same because it's always these same two x coordinates. We have the original coordinate x, and then we have this second coordinate that's h away from our original coordinate. And again, we're eventually going to apply this limit as h approaches 0. We're going to replace h with 0 in our expression. Now again, if I did that right now, just like we saw in the previous slide, we'd end up with 0 over 0. You can kind of look at that and see that that's going to be the case. So we've got some work to do. We've got to make sure that we're working to try to figure out how we can remove this discontinuity so then we can eventually apply this limit so that we can set h equal to 0, and that will eventually lead us to our derivative. So every time I'm going to write down this limit as h is approaching 0. That's core to what we're trying to do here. And so up in the numerator, I'm going to go ahead and FOIL out x plus h squared. Of course, we know that we can't just square the individual pieces. We have to FOIL. So we're going to get x squared plus, now I'm going to get an x times h. I'm going to get a second x times h. So I'm going to get a 2xh. And then finally, h times h is the last two terms. I'm going to get a plus h squared. So that's the result of having FOILed out the x plus h squared. And then, of course, I still have the minus x squared from the second part of my numerator. And then in the denominator, if we just kind of clean house a little bit, we've got x plus h minus x. And so I'm just going to end up with h in the denominator. Those parentheses don't mean much, so my x's are just going to cancel out. So I'm going to do a little housekeeping up at the top here. I still have yet to apply my limit as h approaches 0. And so I can see that I've got these x squareds that are going to cancel out. And so we're left with 2xh plus h squared on the top, and then just h on the bottom. And so at this point, if I was to plug in 0 for h, I would still end up with 0 over 0. But we're now at a point where we can see that we've got some reducing that we can do in our fraction. In the numerator, both of the terms have an h in them, so I can reduce my h's everywhere. I have to do it everywhere. I have to divide that h into each of the terms that I have left in the numerator. And so now I've got my limit as h approaches 0. My expression is now 2x plus h. And so now, if I replace h with 0, I no longer end up with 0 over 0. I've removed my discontinuity by cross-canceling away the h's. And so if I set h equal to 0, I've got my first derivative is 2x. So that is the generalized formula for the first derivative of the function f of x equals x squared. And if we think back to our work on the previous worksheet, when we found the slope of the tangent line when x equaled 2, hopefully you remember that that tangent line was 4. The slope of that tangent line was 4. And so what do we get when we plug in 2 for x into our first derivative formula, we indeed get 4. For the two parts of the problem that you were asked to do on your own last time, so finding what the tangent slope at 1 was and at 3 was, hopefully you remember that those were 2 and 6. And so again, these answers plugging in here or using the technique that we used last time are matching up with our work for that previous worksheet. So now instead of having to go through that kind of step-by-step process that we did at that time, we can use this limit approach applied to the slope formula to end up with the formula, the generalized formula for the first derivative of this function.